Okay, well, so good afternoon. My screen is visible. I'm audible properly. Anyone can answer, please.
Yes, sir, fine.
Fine, thank you. So, voice is clear, Anupam? Screen? Okay.
Yes, sir, fine. Absolutely.
Well, so we were discussing in the previous lecture about the modeling of DC to DC converter. Then we started with the state space averaging techniques. We discussed that there are various techniques. So we will start with state space averaging technique. Then we discussed there are few steps while we do modeling of DC to DC converter using state space averaging technique. So the very first step was that we decide whether the converter is operating in CCM or DCM. Now based upon the mode, which mode it is operating, we have different circuit states. Minimum 2, maximum depends upon the number of switches. So in each circuit states, we derive the state space model of the converter. So state space model in each state is nothing but it is just the inductor voltage equation and the capacitor current equations for each inductor and capacitor available or present in the circuit, right? So once we write these individual equations in the form of a state space model, it looks like that. To separate state space model, as I said, the converter is a variable structure system. So based upon the switching, it changes its structure, right? So we write the state space model in different states or modes, right? Then we next step is that we do averaging of the state space equations using the duty ratio or the time period as the weights for which it is being operated, and we do average over one switching period. After doing so, we get a model which is nonlinear, averaged, and large signal. So as for the controller design, we need a linear model. So we do linearization, introducing perturbations around the DC value. And after introducing these perturbations, we substitute these variable xt, yt, ut, and dt in our this nonlinear averaged model. So these values are substituted such, and these perturbations are such that they have very less value in comparison to their corresponding DC value or average value. Then we have done these derivations, and after that we found that the linear model which we obtained is given by these two equations, and these two equations are having the DC model as well as AC model. So by comparing both the sides of these equations, we can get the DC model and AC model. So the steady state model or the DC model which we have obtained was like this, and these two equations, x equal to minus a inverse bu and y equal to minus c a inverse b plus e into u, this gives the DC vectors, DC state vectors and DC output vectors for the converter under test, right? Then we can obtain the small signal model or dynamic model or AC model for the converter using this equation, and this is the time model, and it is the first order model itself, linearized model. So if we know any control methods which can be implemented or which can be applied to this uh, linearized state space model of the converter, then we can use directly this. But if we know the some techniques which are based, which is useful in transfer function, then we obtain the transfer function. Then considering the initial conditions to be 0, because the definition of the transfer function is that it is the ratio of Laplace transform of the output to the Laplace transform of input when initial conditions are put to 0. So based upon that, we have derived again these two expressions, and we discussed that these two expressions gives all the possible transfer functions in which we may be interested for our analysis and controller design can be obtained using these two equations, right? So we discussed the various possibility of the transfer functions using these two equations, and then we also told that it is not necessary that all the transfer functions should be obtained, right? But yes, the transfer function with respect to duty cycle is very important from control design point of view, that we will see in coming lectures, how to design the controller using transfer functions. All right. So these were the various combinations which could be obtained. We discussed that for a second order converter, 9 transfer functions are possible. For fourth order converter, 15, and for the third order converter, 12 transfer functions are possible. Okay, so we stopped over here in the previous lecture. Now then, we could see that this Si minus inverse, which is called resolvent matrix, it is required to compute in order to obtain any transfer function, because this is common everywhere: Si minus A inverse, Si minus inverse, Si minus A inverse. And this Si minus A inverse is called resolvent matrix. S is a complex variable, right? I is the identity matrix and A is the system matrix whose order is n cross n, which depends upon the order of the converter. Now, to calculate this Si minus A, if I am having the order of the system to be 2 or 3, then it's very easy to find Si minus A first, then Si minus A inverse, right? And apart from that, if all the elements in the converter is ideal, then also it is easy to find the Si minus A inverse. But if converter order increases and the parasitics or the non-ideality is also involved, then what we see that getting the inverse of Si minus A becomes cumbersome or time consuming and prone to error, right? We will see it. Therefore, there are some methods suggested in control literature which, and because S is variable here, A is constant matrix, so the entire Si minus A becomes a variable matrix. So getting the inverse of variable matrix using even computational tools like MATLAB, it is a bit difficult. Therefore, there is a method called Laverre algorithm which helps us to obtain obtain the solutions for this resolvent matrix, which is Si minus A inverse. In normal way, what we do, Si minus A inverse, or not Si minus A inverse, let's say any matrix is there, X is some matrix. So if I need X inverse, then what I do, I take the adjoint of this X matrix, then divide this by its determinant, right? That is the standard way of doing uh, inverse of a matrix. And if X is the constant matrix, then I can just write one small code and I can get X inverse in MATLAB also. But because this X is not constant matrix, like Si minus A is the not constant matrix. So if I am finding the Si minus A inverse, right, for a system, then it will be adjoint of Si minus A divided by Si minus A inverse. As I said, finding adjoint of Si minus A, how we do, we find the cofactors, right? N into n cofactors, n square times cofactors, then we transpose it and then we get the adjoint. Then we get the determinant of this Si minus A, then divide it, then we get it, right? So what you will find that this Si minus A inverse, whatever finally will be a matrix only of n by n, and this matrix will have multiple transfer functions. This will have multiple transfer functions. Si minus A inverse is not a constant matrix, right? So, but what is the alternate way? Alternate way is that according to this Laverre algorithm, which is given in standard control textbooks, Si minus A inverse is equal to Qn minus 1 Sn minus 1 plus Qn minus 2 Sn minus 2 plus like that, and then Q1 S plus Q 0 divided by Sn s raised to power n plus a n minus 1 s raised to power minus n minus 1 plus like that plus a1s plus a node, right? So here qn minus 1 qn minus 2 q1 q node, these are matrices. Basically these qi's are the matrices, right? These qi's are the matrices where I varies from 0 to n minus 1, and these ai's they are coefficients only, not matrices. They are scalars, single value only, constant values, right? And where I varies from 0 to n minus 1. Now our task is to find these qi's and ai's, right? So these qi's and ai's are very easy to find using them. Obviously manual also if it is a small order matrix, and if not if it is higher order, then also it is quite simple, quite easier to use the MATLAB or other tools, right? So we follow the n steps, nth order matrix, so we follow n steps. Step 1 says that we define in. In is just identity matrix of n by n. So if it is like 3 order, then 1 1 1 0 0 0 0 0 0, like that we define the I3. Similarly I4 kind of thing. So we define in, so this is known to us. Now what we do, we find an minus 1 coefficient, right? So what is an minus 1 coefficient? This is minus trace of qn minus 1 into a, right? So a is the system matrix, a is system matrix, and it depends upon the values we have already okay, we will see it now. For buck converter, a is made up of system parameters, so this is constant. This is constant once parameters are defined, right? Now a is known to us, and qn minus 1 a. So what is this? Minus trace. So qn minus 1 is I into a. Both matrix will get multiplied, and this is ultimately a itself, right? So the coefficient of an minus 1, and coefficient of Sn minus 1 is an minus 1. This is nothing but the trace of, we will find trace of a and then opposite to that. So trace in a matrix is simple. It's a summation of diagonal elements. Trace is defined as summation of the diagonal elements. That is a trace. So once we found qn minus 1, an minus 1, so next step is to find qn minus 2. That is equal to qn minus 1, which is already obtained, into a, which is known to us, plus an minus 1, which is already found in the previous step, into in. In is the identity matrix again, right? So why in is multiplied? Because this an minus 1 is scalar, so it has to match with the order of this qn minus 2, which is of nth order. So in is multiplied here. So qn minus 2. Now we found qn minus 2. Now next is an minus 2. What is an minus 2? Minus 1 by 2 trace. Qn minus 2 is known to us now. So we multiply this by a, and we find qn minus 2 into a, and take the trace of this, then multiply it with minus 1 by 2. Similarly, we can find q for at jth step in between somewhere. We can find qn minus j, which is equal to qn minus j plus 1. So you can see here, if it is 2, it is 1. Similarly, if it is n minus j, so it is n minus j plus 1. A is same. So qn minus 1, qn minus j plus 1. It was just calculated somewhere here, one step back, right? So we will use that. And this an minus j plus 1 was also calculated one step back only, that we will use. So that will give me qn minus j. Now after qn minus j, we need to follow an minus j. So when we write the code in MATLAB, then we have to follow the sequence, right? If we do not follow the sequence, then this code will not run. So an minus j equal to minus 1 by j trace of qn minus j into a. Why? Let's say if I'm finding a n minus j, So before that, I should have calculated qn minus j, right? So this qn minus j should come first. After that, only an minus j will be calculated. So this coding sequence is very important. Like that we will do, and finally we will find the q naught. We will find q1 also. So q1 will be like q2 a plus a2 in, right? And we will find a1 also. So this is minus 1 by 1. No, it's a second step now. So this is n minus 1, n minus 1 trace of q1 into a, right? So q node can be found out as q1a plus a1 in, and a node equal to minus an trace q node a. So many coefficients has been found out, and now if we say whether whatever coefficients we obtained are correct or not. If we make some error somewhere in calculation, then how to identify this, how to verify this? So this leverage algorithm gives a tool to check this, right? So what we do, this is the advantage of this, we can verify q node, which is the last coefficient, which is the last matrix, q node into a is already known to us, plus a node. A node is the last coefficient which is calculated into in. So product of this should be zero matrix. So this is a zero matrix, means all elements will be zero, and it's a n by n order matrix, right? So definitely if last coefficients calculated are correct, then it will be zero. If there is some mistake in this, it is not zero, it means this mistakes is coming from previous steps, right? And if previous steps are okay, then definitely this equation must satisfy. So this is the check. So using this algorithm, we can easily find Si minus A inverse. Now we will see some examples of buck converter, that how it can be done. Today in our evening lecture, I'll try to show the MATLAB simulation as well, using some codes, how to get the transfer function easily, right? So this is the buck converter. First, I'm taking ideal buck converter to easily grasp the modeling approaches. So first step is that we will identify, step 1, we will identify the number of circuit states. So we know in buck converter there is only two steps. One is switch is on. So switch is on when we have time 0 to dt and dt to t, switch is off. So we have made equivalent circuit. Now I will not go into detail much because we have already discussed it multiple times. So this was the switch here. This switch is now on. So we just denote the inductor current, inductor voltage, capacitor voltage, output voltage, capacitor current and output current, capacitor current, and this is output current. This is switch on. This diode was here. Battery, this switch was open, so this battery is not connected, only diode is now shorted. So this is the inductor, this is capacitor again, I note, and this is IC, and this is your IL. So based upon these two modes, we can write the state space equation. So for mode 1, we are writing the state space equations. So yeah, so here we can write this VL is equal to V input minus this value. So this is what VC, right? Capacitor voltage. One more thing, when we are writing these models, these equations, then we arrange them in such a way, that on the right hand side we have just the state variable, the differentiation of a state variable, and on the left side we write in sequence. So what is the coefficient of IL here? 0, right? So minus VC plus VG. So in right hand side we just write the state space variable and input, right? So this dIL by dt is equal to, so we will divide this by 0 minus 1 by L Vc plus 1 by L Vg, right? So this is the first equation, right? And you can see this is same written over here. Now second equation we can write, that is for capacitor current, this IC. So this is IC is nothing but IL minus I naught, right? So IC is nothing but IL minus I naught, and IC is C dVc by dt, right? So here you can see I'm writing everything in terms of Vc, not in terms of V naught. Why I'm writing so? Because I want to formulate the state space model where I wish to take this state space X to be IL and Vc, right? That I want to have. So this is IL. Now this I node is equal to, from here you can say I node is equal to V node upon R, but I want to get it in form of Vc, not V node. So this is IL Vc upon R. So this side C dVc by dt is equal to 1 by C IC minus Vc upon RC. So this is our equation 2. Okay. So dIL by dt equal to, so this equation is written over here. So you can see that we have arranged it in such a way that first IL coefficient is there, so it is not present, we have removed, then VC coefficient, then VG. IL, VC, VG coefficient is not there, like that we arrange. And output voltage, this V output voltage is VC. In this ideal case, it is just VC, so we will write V naught equal to VCT. Now these equations which we have obtained, now we want to arrange them in matrix form. So dIL by dt and dVc by dt. So this is making my vector x dot, right, equal to, now this is my x and this is my u, right? So I will arrange this matrix now in such a way that this equation becomes x dot equal to ax plus bu. So first equation dIL by dt equal to, so there is no terms of IL here, so it is 0 into IL. Then there is terms of Vc which is minus 1 upon L, so I have written minus 1 upon L, Vc is here, plus there is a term of Vg, but Vg is taken out, so only coefficient left is 1 upon L, right? So this is the first equation we have written. Second equation dVc by dt, right, that is equal to, what is the coefficient of IL here? 1 by C, that I have written, and coefficient of Vc is minus 1 upon Rc, that I have written here, well, plus, now I need to complete this matrix also. So it's not like that I will not write anything here. In matrix, if nothing is there, then we write it to 0, right? So coefficient of Vg is here 0, right? So we write 0. So this is nothing but x dot equal to a1x plus b1u. I have written in this form where this matrix is a1, this is b1. Okay. Now V naught T. So this is the third equation, V naught T equal to VCT. So this equation I want to write in Y equal to CX plus EU. CX plus EU. So X is IL VC, U is VG, right? So V naught is this one equal to, now IL does not have any coefficient here, so this is 0. Now this is Vc which is having coefficient to be 1, so this is 1 plus 0 into, I can write Vgt. So what is the coefficient of Vgt? 0. So like that I have got C1 and E1 for the mode when switch is on. Now when switch is off, then this was the circuit. I'm again writing the equations. So VL here, this VL here, that is equal to minus V naught is equal to minus Vc, right? So this is L di by dt, which is equal to minus Vc. So from here di by dt comes out to be minus Vc upon L, which I can write like that, di by dt. I can write 0 into IL plus minus 1 upon L Vc plus 0 into Vg, right? And the second equation I form. So this is the first equation. Second equation I can form writing IC equal to, so this is IC equal to IL minus I node, which is V node upon R, and V node equal to VC. So this is VC upon R. So IC is equal to IL minus I node, which is IL minus V node or VC upon R. So this is C dVC by dt, which is equal to IL minus VC upon R. From here C dVC, dVC by t equal to 1 upon C into IL plus minus 1 upon RC into VC plus 0 into VG. Now these two equations, this equation and this equation, I can write in matrix form. So, and a third equation will remain as it is, V node equal to VC, right? So these three equations are there. Third equation is same as V node equal to VCT. I can write them in matrix form. So di by dt, what is the coefficient of di by dt here? 0. Then minus 1 by L, minus 1 by L, then 0. So this is 1 by C, minus 1 by RC, right? And again 0. And for output equation, we know T equal to, this is this equation only, so I can write it like 0 into IL plus 1 into VC plus 0 into VG. So 0, 1, IL, VC plus 0 into VG, right? So this is the output voltage. Now, this is just kind of X dot equal to A2X plus B2U. And this is Y equal to C2X plus E2U, right? So just to explain, I have taken time, but just by looking into the equations itself, we can directly write these matrices, right? So once these matrices are obtained, now our job is easy. The next job is that what we do the averaging. We do the averaging of these equations. So in averaging, how we do averaging? Our A matrix. A matrix is nothing but ABD plus A21 minus D, right? So how to obtain this A matrix? A matrix is A1, this A1 into D plus A2 into 1 minus D. So we'll see both matrices are same. A1 and A2 both are same. So both are same, then I can write A1 only, A1 equal to A2. So A1D plus A1, 1 minus D. So A into A1. So this is your A matrix. Then B matrix, we can write B1D plus B2, 1 minus D. Then B1 and B2 we are having. So what was the B1? 1 by L into 0 D plus 0, 0, 1 minus D. So you can simplify this. This is 0 only. So this is D getting multiplied inside. So this is D by L into 0. What is C? C1D plus C2, 1 minus D. So C1 and C2 are same. So it will be C1 only, which is 0 and 1. E equal to E1D plus E2, 1 minus D. E1 is 0. E2 is also 0. So E matrix will be 0 only. So we got A, B, C, D from here. Now once we got A, B, C, D from here, the next is that we introduce the perturbation and linearization that we do. After obtaining ABCD, what we do? Perturbation and linearization. And after that, we segregate the model and we obtain the SI minus, steady state model, right? So in this case, steady state model, like if you see the value of, what was our steady state model? We derived this formulas. Not this. Yes, this one. X equal to I write it here so I can copy. X equal to minus, yeah, this is the right. Yeah, it is already. Okay, so we can directly use these formulas as well. So what is the A here? A is 0 minus 1 upon L 1C. Okay, 0 minus 1 upon L, then 1 by C and minus 1 upon RC. 1 by C and minus 1 upon RC. A is with us. So our X and B is D by L 0, right? And C is 0, 1 and E is 0. This 4 we have obtained here. So X, A inverse we need here. So A inverse is very easy. If a matrix is given A, like it is A, B, C, D, let's say 4 elements. So in order to find A inverse, we say adjoint of A divided by determinant of A. So determinant of A is nothing but AD minus BC. And what is the adjoint in this case? So adjoint of A will be transpose cofactor of this element, then this element, then this element, and then this element, and then minus sign. And transpose of this will be D minus B minus C A. It means A inverse is just you interchange this elements minus 1 RC 0 and then make the sign to be opposite for B and C. So that is minus 1 upon C. This is A inverse. This is A inverse. Now X equal to means IL VC, that is equal to minus A inverse. So minus A inverse is with us. Now minus 1 by AC, 1 by C 0. B is D upon L into 0. U, what is the value of U? U is just VG, right? So take minus here. Now we multiply this. So this is minus D RLC 0. And in denominator it is minus D upon LC into Vg. So it gives us value dVg upon RLC, and this is dVg upon LC. We are missing one thing here, that is in this is just adjoint only, and we are missing it, need to be divided by this value AD minus VC, which is 0 plus 1 upon LC. So that is multiply by LC, right? So we need to multiply this with LC. So multiply this with LC. So this term will not be there. This term will not be there. So this will be just dVg upon R into dVg x. So it means IL value is dVg upon R and VC value is dVg. Okay. Now next equation is that y equal to, what is y equal to? Cx plus EU, right? Cx plus EU. Now value of E in our case is 0, so this will cancel out. Only C 0, 1, and value of x is this one, dVg upon R into dVg plus 0 into Vg. So it gives me the value of y equal to dVg plus 0, that is dVg. That is output voltage, right? So this output voltage and VC both are coming same. They have to come same because the converter is ideal. There is no ESR, equivalent series resistance, and this IL is DVG, which is nothing but V naught upon R. So this is the things which we can get from here. We got the output voltage relation, we got the average inductor current, we got the average value of capacitor voltage. So it was done with the help of this steady state model. Any doubts so far? Please let me know. Okay. So from here, we got the value of x and y, right? And these x and y may be used later on in our small signal model. So now next step is to find the small signal model or AC model. So step signal model or AC model, which is given by the next formula, which we had this x of s equal to si minus a inverse into d into u of s. This was the formula, right? So here x is IL and VC, Si minus A inverse, and B, because U is now, sorry, one more formula we had, yeah, BD plus BD into DS. So here U is only having perturbation in V. In the nonlinear case, in the non-ideal case, we will also include the perturbation and load current to make the modeling to be a bit complex. So here we are taking the simple only one disturbance, that is a VG, right? So now V output in this case will be C, right? CX plus EU, right? And here BD is VD is A1 minus A2X plus B1 minus B2U. Now we know that A1 was equal to A2 and B1 was 1 by L 0 and B2 is 0 0. So because A1 and A2 are same, so this term will be 0 only. So BD will be 0 plus B1 minus B2. So this is 1 upon L. This is 0 only, right? And U is VG only. So this becomes BD becomes VG upon L 0. Similarly, ED. ED is C1 minus C2X plus E1 minus E2U, right? So C1, C2 are same in this case, so it is 0. Even E2 is also same, so it is 0. So this ED comes out to be 0. So we got the value of BD and ED, right? We got the value of BD and ED. Now next step is to find out this transfer function. We need to calculate Si minus A inverse. Si minus A inverse. Now for Si minus A inverse, first we need to find the Si minus A. So Si minus A is S into I 1001 minus A. Now what is the A? A is this value 0 minus 1 upon L 1 by C minus 1 upon RC, right? So this is S into 1 is S into 0 is 0. So this is 1 upon L, then 0 minus 1 upon C, S plus 1 upon RC, right? So this is Si minus A. Now if we want to find Si minus A inverse, so that is the adjoint of Si minus A divided by the determinant of Si minus A. So the determinant of Si minus A is just multiplication S square plus S upon RC plus 1 upon LC. But what is the adjoint of Si minus A? So we have just find out that adjoint can be obtained. First, adjoint, how can it be obtained here? Just interchange these elements and diagonal elements A and D. So if I have Si minus A, so we interchange this S plus 1 upon RC, and this is S, and then put the minus sign here, minus 1 upon L, and this is 1 upon C. So this is adjoint of Si minus A. So you can see here Si minus A inverse is equal to 1 upon Si minus A determinant, which is S square plus 1 upon RC S plus 1 upon LC, right? And the adjoint is this matrix. So this is our Si minus A inverse using the normal conventional approach, right? So it looks like very easy to find Si minus A inverse because there is two reasons. One is the system is second order. Second reason is that system matrix A, if you see system matrix A, this one, then it has some components to be 0. But if this is ideal, this is non-ideal converter, then we will see that these elements of matrices are not 0. They are non-zero elements. And 0 elements helps us in matrix multiplication, but non-zero will not help. So manually it becomes a bit difficult, right? Anyway, we found Si minus A inverse. So now how to use this, right? So we will put it back. Let's say we want first how many transfer functions are possible. So let's say we want to write first transfer function of IL with respect to Vg, right? Then Vc with respect to Vg. So in that case, we will consider only B, right? First, so here, let's say IL of S, and this is Vc of S is equal to Si minus A inverse B into Vg, right? So Si minus A inverse Bg of S. So I can write it like that. I can divide it in this way. So this becomes IL of S, Vg of S, first transfer function, second VCS, Vg of S. So that is equal to Si minus A inverse into B, right? So Si minus A inverse, I'm writing this value 1 upon S square plus 1 upon RCS plus 1 upon LC, and the next is S plus 1 upon RC minus 1 upon L, 1 upon C, S, right? Into B. So what is B in our case? In our case, B is D upon L, right? We have already calculated D upon L. So we multiply this by D upon L, and this is 0. Okay, so the denominator will be there, and we will multiply this. So D upon L into S plus 1 upon RC plus 0, and the second element will be D upon LC plus 0, right? And this denominator will be common to all. So first transfer function I get IL upon Vg of S, that is D upon L S plus 1 upon RC divided by S square plus 1 upon RC S plus this. And the second one, which is Vc of S divided by Vg of S, that is equal to D upon LC divided by S square plus 1 upon RCS plus 1 upon LC. So these two transfer functions is obtained here, right? Now these are not written here. This is additional which I have derived. Now, if we are interested, so this is with respect to Vg only, right? Similarly, we can find with respect to D also, right? With respect to D also, so IL upon D, we can find IL upon D, we can find IVC upon D, right? So for that, what we need to do for this, what we need to do, we need to write Si minus A inverse into BD. So what BD we have obtained here just now, this BD, D upon, yeah, this VD, that VD we need to put, right? Now we can obtain the transfer function for this V naught upon Vg and V naught upon D. We can find the transfer function for V naught S upon Vg of S and V naught of S with respect to D of S using the same approach. Si minus A inverse B plus EU, that is for this, and Si minus A inverse BD plus EU BD into U for this. So let us say I just find quickly, very quickly, within next lecture is there for this. So for this, this is a transfer function. So 0 into 1 into Si minus A inverse. So 1 upon S square plus 1 plus S upon RC plus 1 upon LC. And then this matrix, complete matrix, S plus 1 upon RC minus 1 upon LC, 1 upon C, and then S into BD. VD is DYL 0, ED is 0 into UBG. Right. So this, if you see, I simplify, this term will be taken out. Right. This term is 0. So this is 0, 1 into, you will multiply this by D upon L, S plus 1 upon RC, and plus 0, and this will be D upon LC, right? So you again multiply this. So what it will be? 0 plus 1 into D upon LC. So this will be D upon LC divided by S square plus S upon RC plus 1 upon LC. This is where is VG? No, this was VG upon L. There is some mistake. VD, what is the BD? VD, value of BD is VG upon L, not D upon L. Value of BD is VG upon L. Yeah, VG upon L, right? So this will be VG upon L. So this will be VG. And this transfer function is same as this, right? So like that, we can see that we can get multiple transfer functions. Now, same analysis we will do for the non-ideal DC to DC buck converter next class, which is at 4 o'clock. Now, if you have any questions, please ask. If you have any questions, please ask. Okay, so no question. We stop over here. Now, next speaker is with us. So we'll start in welcome, sir. Nishan, sir.
Hello, sir. Hi,
Good
sir.
afternoon.
Good
Yeah.
afternoon.
So, sir, like this lecture is just finished. We will have 5 minutes break. Then we can start to 5.
Yeah, sure, sure. No issue with that.
Okay.
Thank you.
Okay. Thank you.
Afternoon, sir.
Hello, good afternoon.
Sir, shall we start the lecture?
Yeah, we can start. No issue with that.
Let me give an introduction.
Okay, sure.
Dear participants, today our next lecture will be given by Dr. Nishant Kumar. Dr. Nishant Kumar is an associate professor in the Department of Electrical Engineering at IIT Jodhpur. He received his PhD from IIT Delhi, where he was awarded the National Best Thesis Award, and subsequently completed his postdoctoral research from National University of Singapore. He also holds MTech degree with gold medal from NIT Durgapur and BTech degree with the Best Technical Student Award from SIT Bhubaneswar. Dr. Kumar research focuses on power electronics, renewable energy systems, electric vehicle charging infrastructure, optimization, smart grids, and digital technologies for energy systems. He has published over 150 research papers, including more than 50 articles in IEEE transactions, journals, and holds multiple granted and filed patents in India and USA. His research has been recognized with several national and international honors, including the Distinguished Teacher Award at IIT Jodhpur, Young Researcher Award, Researcher Excellence Award, POSOCO Award, IEEE Outstanding Young Professional Volunteer Award, and multiple Best Paper and Thesis Awards. He represented India twice at the BRICS Young Scientist Conclave in Russia in 2020 and 2024. Dr. Kumar is a senior member at IEEE and fellow member of IETE and serves a member of National Indian National Young Academy of Science. He is founder and CTO of technology startup SCP Scan, focused on intelligent monitoring solutions for energy systems. He is actively engaged in international academic collaboration and regularly contributes in global research and capacity building through invited academic engagements. Now I request Dr. Nishant to please take over the session.
Thank you. I hope my screen is visible to you all.
Yes, sir.
Okay. Yeah. So before going to start this session, first of all, I'd like to thank the MNIT Jaipur for giving this opportunity, and also I'd like to thank the Dr. Garg for inviting me for this FDP, and also all the volunteers and involved every faculty members of the MNIT Jaipur who is dealing this FTP, and I welcome you all, the participants who are here. So in today's discussion, I will discuss mainly about the digital twin technology. The title of this today's session is the physics informed and data driven digital tune for high power converter. So, and the converter applications we will see for the renewable integration or maybe EV chargers. So wherever you want to use this power converter, you can use it. But yes, the most important thing is here digital twin. So entire discussion will be based on that. So first I will start from the basics, and then basics means the what is the history of that, and then I will come on the basics means what is the physics behind a physics based digital tune for converter, and then related equations, mathematics, controls, and all these things we will see, and then come back to the data driven digital tune portion. Like that way, in two part entire session will be performed. So whenever you feel a question, you can ask. Maybe question at end or maybe in between. No issue with that one. Anyway, so the first, the term, the digital twin, which is looking new. I think this is new terminology for nowadays everyone. Also for me also. Uh, before this digital tune was not that much popular. Digital system was popular, digital platform was popular, digital controller was popular, but digital tune came in picture recently. So the digital tune is mainly it is a virtual replica of a physical system. Virtual replica of physical system means so whatever the things is happening on the physical system, the same thing we will see on our digital platform. Uh, so in another way, I will say that. So similarly, we are doing the simulation and then hardware. So what is difference here? Difference is during the simulation, what the results we are getting. That is not exactly very similar like a hardware, right? Because on the hardware, whenever we are running, so many disturbances are there, noise, EMI, practical line components also. For example, we are using the wire or maybe cable or whatever the components we are using. So the components have internal inherent resistance. From here you will see the inductance, capacitance according to the different devices which we have placed there. So all those things are going to create some issues, noise, MI impacts, and all that. But whenever we are doing the simulation, those are not there. In simulations, most of the components are ideal and the components are behaving like a practical one only when we are putting the additional information and then modeling the components according to that, then those things will be come in the picture in our simulation. But here our target is to we will link the simulation platform and hardware platform through the sensors, through the cables or through the communication channels, and we will use those sensor information of the hardware platform, and then mathematically we will tune or mathematically we will derive the performance, and then we will see the what is happening on the physical system. The initial goal is initial I will say the two part is here. First part is how many sensors we are going to use for this purpose. It's very clear in this digital twin platform we will not use any additional sensor. What are the sensors are available on the hardware platform, exactly the same similar hardware sensors will be there, and those informations we will take on our digital platform to do our mathematical analysis, and then or we can say that our virtual platform building. Nothing else. We are not going to place any additional one in the first phase. Why this is? Because see, since this technology is new, and then hardware platform, for example, a PV park or maybe a AV charging station or maybe windmill is already running on the ground. And if you will say that, no, I am going to place one additional sensor there, it means you are going to disturb the network or you are going to place or insert an additional device there. But hardware is built by a certain company. Company have given a some certain warranty guarantee. And with these limitations that you will not disturb the hardware component there, right? If you will cut the wire or disturb the network or you will place any additional components there inside the circuit, then those will violate. So no one will allow to do that at the initial stage. So the first limitations is what are the sensors by default there. So only you can take those output also because those sensors are there for what? For control purpose. Because those sensors are sensing the information, giving to the local microcontroller, and the microcontroller taking the decision and then running the firing the converter, operating the converter according to the condition. So those informations we can take outside for our virtual platform. The first is this one. Second part is once you will get those sensors information, then you have to use your mathematics or whatever your system you want to use it so that the performance or output, whatever the output we will derive, so that should match with a very high accuracy with the practical system. Means here, so suppose through the mathematical sensors, so mathematical analysis, we will derive the inductor current, inductor voltage, or maybe DC link capacitor voltage we are going to derive, or DC link voltage capacitor current we are going to derive, or maybe switch level voltage we are going to derive. So these derived, or I will say that this output of the digital platform should match with the practical one. Means by using the probe, when I will measure the voltage there at the same time on the inductor, on switch, then this should match with this. then only we can say that okay, now these two both are tuned with a very high accuracy. How much should be the accuracy? I will come on that when I will discuss about the standards. Then you will see that according to standards already derived, so how much percentage it should match. So that is your first phase of the digital tune, means introductory level. And then once the both will start matching, then by using these information, we can go for the next level. Next level means for the fault analysis, maybe the health component health monitoring and all those things. But initial stage is this one, means create a virtual replica of the hardware or physical system, and then here the performance of both should match with a high accuracy, means exactly always more than 90%. It should match, right? So this one. So if you will see that how these things evolved with time, so this is exactly not a new thing. The history or past of this technology is very old. So it started from 1960s. So that time NASA invented these things and started using for spacecraft. So that time these things was for the spacecraft. So what is happening inside the spacecraft? They was taking the census informations and then simulate on the virtual platform in the lab and then relate those things and try to predict the fault and issues, what other things is happening there. Then slowly after 80s, in the year of 90s, the some other companies came in the picture and they started to using these things for the product life cycle management purpose. But still these things are under the control of NASA. So still this is a government control, not the private one. But yes, initially few private company involved here and then try to develop these things for the commercial level for the life cycle management. But still the component where they are using, those are related to the spacecraft, because this that time the technology was costly, so the monitoring should be also for the higher costly thing. If our protection circuit is costly, so definitely we will use those protection component, or I will say protection mechanism for the costlier item, not for the cheap item. So that time spacecraft was the one of the costlier items. So these things were initially you started using for that, and then also we started coming from the manufacturing plant level related to the spacecraft components. Then in 2000 and 2010 in between, so some other companies also came in picture, and then also little bit liberal behavior from NASA came and then started giving the insight information of the digital tune and start sharing this information with the academics, and then academics also involved here to grow this the secret digital tune technology, which was initially concentrated over the spacecraft. So through this way, these things came in the picture. Researchers started using very frequently in the lab, and then they started building the sensors, signals, IoT technologies, and for industry level as well as for the your NASA applications level. So in 2010 onwards, you will see that NASA started publishing the papers, publishing the white papers also, so many patents and all these things came in the market. And then also new technology, IoT, cloud computing, big data platform. So all those things started using here. And then since this time processor cost was low, so that's why application was also on a vast level. So currently, so initial days, this was only for the spacecraft, but after that, 2010 onwards, all our manufacturing plants, all our data centers, and all those was ready to take this thing, these components. So slowly it came and started coming in the market. And so that's why this era is called the birth of the modern digital tune. And then in 2016, Industry 4.0 started recognizing these things, and industry also ready to take it forward. So after that, digital tune started using very frequently in the industry level, especially for the predictive maintenance and lifecycle intelligence, health monitoring, fault analysis, and all those things started happening. So especially still for the energy manufacturing and in the healthcare little bit. So like that way. So this was the era, and then in currently 2021 onwards, this is on the next level. Now we are also integrating the AI here, and what is the use of AI here? Since system information we have, then we can monitor it continuously throughout the year and 2 year, 3 year, 4 years. Then easily we can say that what is happening with time, because day one when we are looking on the performance of the component or the device, then definitely some certain, for example, if we have a car and the day one we are running our car, and then definitely we are getting some certain efficiency, certain performance efficiency in the terms of fuel performance, in the terms of the vertical vibrations and other things we are observing, fine. But after the 5 year, definitely these things are going to deteriorate, right? So if we are monitoring continuously, then easily we can say that with time how these things are deteriorating, who is responsible for that, and also we can think about the possible backup plan. So if possible, we can improve or something like that, or also we can predict the future after a certain how many years this device or this vehicle will not compatible or not useful. Useful in the terms of money means, if your, suppose for example, if your fuel efficiency is going to deteriorate significantly and your per kilometer cost is increasing significantly, so after a certain time you will realize that the cost is not bearable. So that time definitely you will try to throw the your vehicle. So like that way. So here AI is using for that, means continuous monitoring for a long time and then predict the behavior for future, and then think about the possible take care in between also, so that system will okay for a long run. So like that way these things is happening, and then researchers are working over that. Another is the, whenever we are going to think about the industry, so definitely standard is also one important aspect here. So a standard size, the most popular standard is ISO 23247. This standard mainly related to the manufacturing plant, and then here this standard says about the different aspects of that. For example, you can see here the six part is given. First part is telling about the overview and general principle of the digital tune, means so how you will integrate and what should be the basic principle to integration with the physical system. Second is the reference architecture or the functional view. Reference architecture means the sensors, where you will place the sensor, what type of sensors you can use, and what type of sensors you cannot use, or what type of architecture you will follow or not. So those information is given in the part 2. Part 3 is related to the basic information attributes of the observable manufacturing elements, means which component, means definitely whenever we are going in the manufacturing plant side, so some portion is definitely something is secret there, some is related to the third party uh, uh, provider. So so that time secrecy of that those devices should maintain, right? So for that purpose, this part 3 will justify, or I will say the give the guideline where you should monitor or where you should, which portion you should avoid according to the plant, and then the contract between the service providers. Part 4 is related to the technical requirement for the information exchange between the reference architecture. Here technology requirement means the you are going to transfer the data from plant level to a control room. So here, what type of technology you are going to use? Technology is IoT, or maybe wireless communication, or simple you are going to use a cable, means Ethernet wire, or maybe a fiber optics we are going to use. So what type of technology we are going to use, and then during this during this data transfer, what architecture we should follow for the data security, means encryption or decryptions. So those things will also here, because this technology requirement will directly link to the cybersecurity. So that's why this is very important. And because plant will be definitely on a certain location, and then control room will be somewhere certain location, and then digital twin platform will be in the control room, and plant is running on the ground. So that's where you will see a significant gap. Here, this things is very crucial, I will say that. So encryption, decryption, and then the communication channel in between. Suppose you are going to use, if distance is high, then in between we will use the boosters also. The how many boosters should be, and then booster will increase or decrease or boost the component, sorry, data at what level. So all those things you will see in part 4 they have given. Type, so sorry, part 5 of 5. This one is related to the distant thread for the distant tune. So here the In these sections, you will see the sections. So by using the information in the control room, what are the things you are going to do? Means health monitoring, or maybe your uh, planning for the I will say the maintenance planning, or maybe fault detection, or maybe health. So what are the things we are going to do? So all those things will defined here in part 5. Means objectives of the digital tune, or objective of the investment. And part 6 is related to the composition of digital tune. Means this is assessment, final assessment after the certain investment, how much benefit we are going to get annually in the terms of money, time, and other aspects. So this part 6 will yearly justify, or I will say the yearly through audit, it will justify. So digital tune, using the use of this digital tune is justified or not. So the part 6 is related to that. So this annually it will happen through the audit process. Like that way, these things are derived here in this framework or in this standard. But for a renewable application, or I will say the EV side or charger side, we can follow this ISO or IEC 30173 standard, which has derived in 2023. So I think this one is the most recent one with respect to the other. So this one is this standard actually given the or I will say the derived the basic concept first, and then divided the entire component in three three entities, maybe we can say that. And then for the every entity in this standard given a certain guideline. Okay, so here the first is the basic concept. This standard just tell about the definition. What is the basic definition here? Digital tune is a digital representation of a target entity. Here the target entity may be a component or maybe a system, right? It's synchronized with the real world counterpart through continuous data exchange. Through continuous data exchange means 24/7, and it will synchronize and then represent the target entity on the digital platform. This one is the basic definition of through this, I will say, the standard. Here the derived entities are target entity, digital entity, or synchronization. So here the target entities may be the plant, for example, solar PV array plant, maybe windmills, maybe battery, EV, or maybe charging station, or maybe controller device. Anyone can be considered as a target entity. Means digital tune is going to build for what? So that is your target entity. Another is the digital entity. Here the digital entity is the real-time model simulation, simulating power flow, efficiency, or degradation. Means you are going to use your digital tune for what purpose? The purpose is to see the power flow, see the efficiency, or maybe regulate the efficiency, or maybe the health degradations, maybe performance analysis, stability, cyber security, or all those things. All this one is the target, or I will say digital entity. Means output of the digital, I will say the mathematical models or mathematical analysis. Those are our digital entities, means output. And synchronization is the process. In the synchronization process side, here you will see the live monitoring, fault detection, prediction control. Means to achieve the digital entity, what the process you are going to follow, those are synchronization, right? So here you will monitoring is one of them. Another is your, you can say, the fault detection techniques. So what techniques we are going to use, and how those techniques are going to use those data, what the data is coming from the plant, and then how those are going to use here. So those things you will see in the synchronization slide. And this one provides a standard framework for the integrating hybrid energy components within the unified digital twin architecture. So this standard decides all these things, and then accordingly we have to perform those things. So also I will show that. So for a converter side, so when I will discuss about the converter, so that time you will see the target entity will be converter. What is the digital entity that time? Digital entity will be there. So you will see the performance or the efficiency. Sometimes you will see the stability also I will showcase. So those things will be the digital entity. On the synchronization side, what method we are going to use? So for example, I will discuss the time domain digital tune technology, or maybe frequency domain digital tune, data driven digital tune. So those will be considered here, or maybe mathematical modeling, control techniques, optimization, whatever we will use, those will be under the synchronization process. So like that way, you will see those things. So all these things are okay related to the basics, but come on the evolution. So this one not evolved directly, right? So this is the evolution from a time. So mostly you will see here is a three things. So digital tune is the last one, but before this digital tune, first was the digital model. Digital model was already in our society, and we all were using those things. Digital model means what? Where we have a physical system, where we have a digital simulation model, or digital platform for languages. For example, we have for example, we have a simulation. Suppose you are doing a simulation of a EV charger on your MATLAB in your computer, and then similarly you are building a hardware in your lab, for example, or maybe on the ground you are looking at charger. That is the hardware of that. Okay, but both are completely separate from each other. Maybe that this time you will see the so many components you are not considering in your simulation, but during the hardware those things are there. Similarly, you will see that during the simulation, so rating may be different, hardware side rating may be different, but no link between the hardware and this. But yes, basic idea, rough structure, and all these things you are analyzing through your simulations. So that is the digital model, means here no link between them. If you want to suppose link them, then what you are doing, then you will run your hardware, generate the data, and then those data feed in your digital platform or in a mathematical model manually, and then you will see the performance, and then if you will get anything, then you will feed in your digital model. Basic example is something like that. Suppose if you have any plant, and then plant have a PI controller, and you have to tune the PI. Very simple, I'm taking KP. So your target is to find out the value of KP and KI or KT. So how you will get it? Definitely, we all know that slightly we will shift here and there and randomly trigger, and then finally we will tune it. We all are doing these things. But suppose you are going to do these things by using the digital model, then what you will do? Then simply you will simulate the system in your MATLAB, and then here you will see the KP, KI, KT, and then you will use this one in your hardware platform. But yes, this will not work there. Definitely these numbers are not going to work, but this is very clear. So those number will work there, that will be close to this. Means a rough idea you can get from that, means ki will be 1 or maybe 100 or 0.1. So those whatever the number will be there, that will be very close to, we can say that, to our simulation session. And how much close will be, it will depend on your simulation, how your simulations you are doing, and means you are taking the same rating or not, and you are taking the similar component or not. So if you will go for the more and more realistic one, then you will see that these things are chances of matching will be more and more closer. But yes, not exactly. So it's like that. So that is the digital model, means physical and hardware both will be on a different platform. No data exchange between automatically, and manually you can do that. Then came digital shadow. Digital shadow is the another platform. So here you will see that, so your digital platform will receive the data from the hardware, and then you can visualize it or you can analyze it, but you cannot feed back. For example, uh, our DSO is a one platform where, and hardware is one physical device. On hardware we are placing our probe, and through the probe is just like sensor, right? So through the probe we are sensing voltage and current, and taking on our DSO, and then on the DSO we are visualizing the performance, how the voltage is increasing, decreasing, fluctuating, or similarly the current, everything, maybe power analyzer also, so you can see the power behavior and all that. But if anything is happening here, suppose wrong, then your DSO cannot take any action over your hardware, because this is just for the visualization. So that is your digital objective, the digital platform. So that will come on the digital side. So your digital platform has not capable to feed any backup information to the physical system to take the corrective action, right? But in the digital tune, you will see that here both have two-way communication. Means you can visualize, you can analyze, as well as if required you can give a command back to the physical system, so that physical system can take the corrective action accordingly. So here, so definitely here you are not going to use the DSO. Definitely here you will use a computer, you can say like that. So you will take the voltage, current, whatever on your computer, and you will visualize the waveform and all that. And if you realize that waveforms are performances are not according to your choice or your expectation, then you will give a command to change the control action, right? So, and then your controllers are changing on the hardware side. So hardware has a controller, and the controller is changing the things according to your given command. So this will call the two-way communication. And this time we can say this is your digital twin. Means physical system and digital system both are communicating with each other. This is very similar like a smart grid. Traditional grid and a smart grid. What is the difference there? This one is the difference, right? So two-way communication between the operator side and then our load side. Okay. So in the digital twin ecosystem, so I think up to here we are familiar with the digital twin terminology. So in the digital twin ecosystem, mostly you will see the two, three things. One side you will see a physical world, a real world, you can say that. Real world means the plant. So whatever plant you are expecting, you can think about that. Plant may be vehicle, plant vehicle charger, maybe the converter, inverter, whatever. Means physical system. Another side you are going to use your digital side. So here definitely required one computer or maybe a processor. So that should be, and some algorithms. So some algorithm or maybe mathematics, we can say like that. And also required some data storage here, because both real world system and the digital system are going to link with each other through sensors. Sensors are going to give the information of the real world system or physical system to the digital one. So here we will record some, suppose we will do the method. We are not going to record the 100% data, but suppose we are analyzing something and then key points we are recording also, like that way. And also you can say that suppose you are someone is going to visualize that one supervision actually. So that time suppose we have a screen, then the data will fade on the screen to visualize those things also. And then if required a counter action, then this counter action will go inside the physical system through this acquisition model, like that way. So here you will see these three things, right? One side we have a communication, means sensors, actuators, or I will say the cables, whatever. Another side we have physical system. Another side we have a digital platform with computer and so many algorithms, and then also screen, and then data logger system, or maybe data storage system, whatever you can consider on the digital side. So this is called the digital platform, and the entire will call the digital tune ecosystem. This digital tune is also, as I told, this is not new. So here the maturity of the, suppose you are going to build a digital tune for a particular system, so maturity is also important. So whenever we will build up this, then we will decide the maturity. So this developed digital tune is at what maturity level? So this maturity level depends on the performance capability. So the first, the total you will see the four, just like in EV, we know the ADAS system, right? So ADAS level 1, ADAS level 2, ADAS level 2.5, 3, something like that. Also ADAS level 4, where the system is completely auto, uh, 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 no need of any driver, right? Complete automations you will see there. So like that way. So different ADAS system. Same thing is also here. Digital tune have a different level, and this is called the digital tunes maturity level. So level 1 is related to the basics one. Basics one means here you will see the, if you have a if, and then this one, this all this maturity will depend on the digital side, not on the physical side. Means your algorithm capability will decide this maturity. Means by using the different mathematical modeling or mathematical technique, how much information you are capable to extract, those things we are going to see through this maturity level. So for example, the first one is related to the basics report and analysis. It means that whatever the data you are capturing from the physical system and taking on the digital one, and then you are analyzing, those are very basics. For example, you are looking on the dynamic low fidelity model, or maybe dynamic power variations you are analyzing, or simple you are visualizing the waveform, capturing the performance, right? So those things if you are doing means basics one, those will be called level one, but no capability of automation decision making. Means here your system does not have capability to take a decision counter action against any fluctuation or any disturbance. So in your level one, you can visualize that thing, and if you feel yes, this thing should change, then you will trigger, then only those action will taken on the physical system. So in the level one, simply basic learning, data assembling, and all these things we can visualize on our platform. And then one, definitely some suggestions you will see on your pop-up suggestion will be on the screen, but if the operator will trigger, then only those things will pass to the physical system to take the counter action. This is your level one. Level 2 have a advanced reporting and analysis and forecasting. Advanced reporting means here the sometime you will capable to capture the real time dynamic information or some dynamic. First thing you will see here, so data fidelity will be on a very high rate so that you can dynamics or transients, a small variations also you can capable to capture. First good thing. Another is the you have a basic analysis and forecasting technique, so that by using the by using the performance you can forecast for the future. For example, if you are operating inverter, then you can forecast after a certain year or after a certain time what will be the performance of that. This forecast is also called the uh, state of health, we can say that, health of the inverter, health of the switch, and all that. Or maybe we can say predictions also. Those things you can do here by using those informations. Okay, so those will be on the second level. So here you will see the advanced predictive analysis, advanced data assembling capability to ensure the convergence and accuracy. So those things we can see here in the second level. Third level is little bit higher. So here it will support the strategic decision making. Strategic decision making means this time your system will capable to decide a strategy to handle a particular issue. Issue may be related to the cyber threat or maybe any disturbance from the load side or maybe source side. So here your system will be capable to decide, make a strategy to handle that, and then it will feed the information to the system and take the action automatically. No need of any third party to trigger, then only action will take it. So here those special things you will see here. So is suppose if you have a single unit, then this level 3 is sufficient to run the system in a autonomous mode. No need of any additional. This third level is sufficient for that. So all the features you will see here, self-efficient. Only lag is in the level 3. So level 3 is self-efficient. Level 3 is not going to care about the neighboring plant. This is the only drawback here in the level 3. Means, so suppose in the nearby plant, if anything is happening and then required support from the neighboring plant, so level 3 is not going to help them, because level 3 is not going to communicate with the neighboring plant. Means coordinated control you will not see here. This is completely primary control, and then primary, according to the primary control, it will always try to fulfill the objective, demand, whatever things are decided like that. But in level 4, you will see that this is autonomous decision making system. So here you will see all those objectives. Here is the multi-scale system, dynamic system you will see. Means here not only for the plant, also neighboring plant, this system will also communicate with them, just like a secondary control of the converter. So get the data and then take the decide the strategy and then take the action jointly. For example, if you have a grid, right? Suppose if you have IEEE 5-bus grid we have, and in IEEE 5-bus system we have 3 generator. Suppose each generator have digital tune, suppose, and then 4 loads are there. So loads are increasing and decreasing. So which generator should feed what amount of power, what amount of active power, what amount of reactive power. So this thing should reside in through a coordinated discussion. So in level 4, those things are possible. So each plant will share the information with each other, and then jointly they will make a strategy and take the action according to that. As well as here you will see the state of art analysis and variations. Means AI in machine learning is also going to use here to decide the future predictions and all that. So in level 4, this is the highest mature level. Okay, so this one is the related to the basics of your digital tune. Next is what I'm going to discuss here in detail is a set of digital tune for the converter side. So in this converter system, I'm going to use source as a solar PV, right? And output side I have attached one grid, and then on the PCC of the grids we can attach our EV. So we can say that the AC charger, suppose you want to say, you can say that this is a AC charger, or you can attach on the DC link. So you can say that DC fast charger, whatever terminology you want to use, you can use according to that. So here if you will attach your charger, so that time you will call the AC charger, here you will attach the DC charger. But those are just like a load. But the system, basic physical system is just like that. PV array, here we are going to use one DC-DC boost converter, then you will see DC link capacitor, then 3-phase inverter, interfacing inductors, filters, and grid. This is a complete system. This system is called the physical system. So also we will see the load here. Where is the load? Load may be DC link, load may be here. So those load will be also, and all load and then all these components will consider as a physical system. On the other side, we have a digital platform. In the digital platform, we will go through the sensors. Where is this sensor? Sensors will be placed here somewhere, right? So all those sensors, communication channel, and then computer or HIL system, whatever the system we are going to use, both. Means all those sensors here and there, and then communication channel and link with the computer, like that way. So this will consider as a digital platform. But since the sensors can be considered on everywhere, means on the both places we consider our sensor. Without sensors, this system will also not run, because here we have inverter. If you want to control the inverter, so required some sensor to feed the data, and then here the inverter control will go through the logics and generate the pulse to operate it. Similarly, boost converter, here we have another controller, right? Required some data to decide the switching pulse for the switch of the boost converter, then only it will operate. So definitely some sensors are going to use here. So those sensors will consider inside the physical system as well as inside the digital platform. So in picture wise, the complete system, so suppose a complete system will look like this. So here you will see one solar PV panel, you will see at this stage. Here we are using one DC-DC boost converter. This boost converter is attached with the solar panel, right? And then here we have a DC link capacitor, this inverter, and then this one is the controller, and then interfacing inductors, ripple filters, and then this is the grid. So in this entire operation, I'm not talking about the digital twin, simple operation requires some additional sensors also. So what are those sensors? Grid current, grid voltages, DC link voltage, and then here suppose we have a load, the load currents will require. So if loads are here, so AC side, the loads will be here. So this is the load actually. So here the loads are going to attach. So these are the loads. The load current will also required. Another side we have a DC link. So if you want to attach the load on this side also, fine, you can attach also here. Another side we have a, since we have a panel here, so this will require one MPPT algorithm, and then MPPT algorithm will decide the pulse for this. So here again required some sensors here also, means DC PV voltage and PV current. Two sensors are here, and then this side you will see total of 10 sensors. Right? 10 plus 2, total of you will see the 12 sensors. If you have a load, then you will see the total of 12 sensors, or required only if you don't have load, then you will see the total of 9 sensors. So the first objective, as I told initially, so this is a plant which is built by some certain company, so you cannot break or disturb the circuitry or operation. So if this is a 12 sensor based with load, then your digital twin will use all these information, 12 sensors. And then if this is 9 sensors based, so you will use all those 9 sensors information. No any additional sensors are there here. You cannot place any additional sensor here. You will not cut or place anything. Okay. So in this, I'm coming on that, how this will work and all that. So if I will come on the motivation, why this work I'm discussing here, this is actually, this is important actually. So in India, we are moving for the 500 grid enable, or I think you all know. And mostly this is not that much important. Important is this project, because funding is very much important for the research. So I have two projects.
Your voice is not audible. Your voice is not audible. Shant?
There is some technical issue is reconnecting. Okay, so be connected, please.
Uh, Sorry for disturbance. I think I am visible to everyone.
Yes, sir. The slide is visible,
Okay, thank you.
but you are not on this slide.
Slide is not visible.
Hey, you are, sir. You are not on this slide.
So
Yeah, definitely I will come on that. This was the slide.
Ah, yes, sir.
I was here. Yeah, just previous slides. Yeah. Okay. So definitely. So I was talking about the motivation why this is. Definitely this is because of the projects what I was talking, nothing else. So I have two projects related to that. So that's why my complete group is working and focusing on that. So that is not important. Important is this one. So standards. Whenever I will discuss a different digital twin results and all that, so that time you will see what basic accuracy we should achieve at least. So here we have two things. One is the ISO 23247 and IEC 617241. This standard says that if you are applying your DT or digital tune, the short form of digital tune is DT. If you are applying your DT for performance monitoring. So that time at least your accuracy should be 95%. 95% accuracy means your performance matching should match will be 85%. Performance matching means means waveform by waveform. Your accuracy should match, or your performance should match, your waveform should match 95% plus at least. On the side, we have a ISO 23247 plus IEEE 1547. This standard define the stability analysis. And if we are going for the stability side, stability analysis by using the DT, so that time, anyhow, your accuracy should be more than that. So this is the two important thing. So whenever I will discuss about the results, so that time this is, yeah, one confusing point is here also. So whenever you will go for the DT, there you will see two things. One is the data inside the control room, data on the ground. See, both are different. Data on the ground means what is the current voltage there on the plant level. That is the one number. Another number is you are getting in the control room, means data you are sensing. Definitely you are using a sensor. Sensor have a certain accuracy. You are going to lose something. And then you are going to data your boost up, and then, or I will say filter, then convert also means during the encryption you will convert it and encrypt the data. Then you will pass the data from through your communication channel and receive on the receiver platform. Then you will again encryption to decryptions, and then this decrypted data will again filter out and then boost up, and then you will use it. And then definitely in both the platform, both side you will see analog to digital converter, another side you will see the digital converter, and then all those things. So everywhere you are going to lose some amount of accuracy. Those accuracies are not going to consider here. According to these standards, whatever data you are getting control room, that you just consider that is 100% accurate. And then with respect to that, compare how much accuracy you are gaining through your DT. Means data room is everything. Don't go on the plant level. If you will go on the plant level, then all the small losses you should consider, right? So those, don't consider those things. Consider your data room or your control room is 100% accurate, and then with respect to that, define your DT. How much you are closely you are going to match that. And then another side, not only our lab, so many companies are also working in DT this area. And then some score I have shown here. So for example, GE, Siemens, all big company, Ansys, Microsoft, Siemens, Dassault also. So they are also working on this DT side for different application. Application is different, but yes, they are also trying to develop the DT for a particular specific plant, and then pilot level they are testing on these things. So what accuracy they are gaining? So you can see here. So always they are claiming 98%, 99% accuracy. Everywhere they are claiming. Fine. So our research is also motivated through this to get a high accuracy for that. Okay, leave that, come on the system. So in this discussion, what the system I'm going to discuss, that is this one. So one side we have a solar plant, boost converter, inverter. Means mainly I'm going to inverter side. So then you will see the filters and then grid. So what is happening here? The system is running, and then power is flowing, and then power is going from here to here. So this is the power flow, and this complete setup will consider as a physical system. And then everywhere you will see sensors, as I told initially. So all the sensors are for the control unit. So those sensors information will also come here, and then through this your communication channel, this information will also come on the digital platform. So here this digital platform may be a computer or maybe our HIL platform. So here we will do all those analysis. So this is the basic structure of the physical system. So always you will see the two part. One part will consider as a physical system side. For example, here this was the solar PV panel, boost, DC converter, inverter, filter, and all that. And digital platform side, when you will go on the computer side, there you will see the mathematical model. The mathematical model side, again you will see the 3-4 part. The first part will be your mathematical equations. Suppose you are going for the physics based, and first I will try to deal the physics based DT, and then I will come on the data driven. The physics based, first you will go for the basic mathematical analysis. You will write the equations based on the physics, and then you will discretize. During the discretization, you will go for the, you have two options, time domain or frequency domain. So according to the your choice, you will pick the domain, and then accordingly you will discretize those things, and then you will, and then whenever you will discretize and all that, you will see so many unknowns are here, right? Then that time required some initial values for that, and then you will go for the optimization technique, and then try to get the all the values of unknown parameters. And then once the unknown parameters values will be in your hand, then your mathematical equations set of equation will form the dt set or dt equation set, like that way. One by one I will come over that. So first write the physics based equation, then discretize, and then physics based equation whenever you will write, then that time you will see so many unknowns are going to come in the picture. For example, you have no idea about the line resistance, you have no idea about the actual inductor. Even in this picture, you know you are using one inductor here, so that and you also know that this is a 5 millihenry, but that is actually 500 millihenry, or this is 4.99, or this is 5.01. You have no idea about that. Also, if this is an inductor, then what is inside the inductor? Some internal resistance is there, but what is the value of that? So you have no idea about that. Also, during the time when the temperature is increasing, that internal resistance is going to vary. So again, you have no idea about that. So what you will do, so whenever you will write a physics a basic equation, so that time all those unknown parameters you will consider as a one variable, nothing else. And then through this optimization technique and parameter initializations and unknown parameter classification, your target will be find out the actual value of that, so that waveform should match with a higher accuracy, which is called the 95% plus. This is the basic fundamental of any DT. So whenever you are going to format a DT. Okay, so here mainly you get the two approach. The first approach is based on the physics based. Physics based means here you are going to write the complete equations, a big KVL, KCL you will apply, basics one, and then you will write the equations, and then discretization, and then you will do that. And here you have the two options, as I told, time domain based equations you can write, or maybe frequency domain based equations you can write. Both options are in your hand. You can choose according to your choice. And the another side is your data driven based. Data driven based means this is a specific one actually. Data driven digital tune is not, I will say, the not uh, suggested for the actual plant. Data driven digital tunes are mainly for the research purpose. Means suppose someone does not have the plant, or suppose someone does not have I will say lab prototype system. So that time what they can do, they can take the data directly, data set from an open platform, download those data, and then apply your data driven digital tune there to test your basic equations, whatever the equations you have developed, that is correct or not, what are the your machine learning technique or whatever the soft computing technique you are going to apply here, so those are correct or not. So for that purpose, this means data driven digital tunes are mainly for the research purpose, or I will say the teaching purpose. But in the physics side digital tools, this one is mainly for this one is mainly for the your research purpose. So here you will see the time domain based, time domain based and frequency domain based. Which one is good? Through the result we will define. Both have one merit and one demerit. First I'm coming on the time domain based digital. Time domain, discrete time domain based. Discrete time domain based means here the whatever the equations we will write, that is in the terms of time. Okay, so first we will see we will go for the physical system, very similar, and then what are the sensors we are going to use. So those will consider as a sensor data, those will consider as a known parameter. Whenever I will say the known parameter means all the sensors which is here, means sensors are there, it means you know the value there, what is happening there on every instant. So that's why these are called the known parameters. For example, VPV, IPV, VDC, grid voltage, grid current. If there is a load, then all those load current. So all sensors you are using, so those are known for you in the entire journey. These are known. What are unknown there? Accept this, what are the component you are using there, and if you want to see the performance or analyze the performance of those component, then the voltage and current across or power across those component is unknown for you. For example, you are using inductor on your just behind your inverter. So, and you have a three inductors, right? And your target is to analyze or see the behavior of inductor. So, inductor voltage and inductor current will require. So, but you have no idea because your sensor is not for that. So, those will consider as unknown parameters. Similarly, you have a filter, a small capacitor and a small resistance you have used there. So, those will consider as unknown parameter. Similarly, you have an inverter. Inverter has 6 switches or maybe 8 switches or maybe single phase. Then you have a 4 switches. So if you want to analyze the each switch, then required voltage sensor and current sensor there for each switches. But you are not using. So those will again consider as a unknown parameter. Like that way, you will see a 30-40 unknown parameters in the system, right? So those will be here. And these are sensors. And your target is write the basic physics equation by using the KVL KCL and then go for the, but whenever you will start writing the equation, so that time you will not write directly L or R directly. You will use a small thing. I'm coming on that. For example, this is the picture. So whenever you will start writing, so for this one, so whenever you will write a KVL here, so that time you will consider this L dash and R dash. This L bar or R bar, those are R bar is the internal resistance of this inductor. This L is bar is the inductor actual inductance of this inductor which is in the boost converter. Similarly, you will see this side, this one. This is LR bar means inductor of the filter. Similarly, RR bar. So this is the internal resistance of that. Wherever you want to analyze, you will make a system like that. Suppose this is diode. So how you will write? Diode have, you know, that whenever diode will trigger, initially one small voltage drop happens and then you will see a continuous conduction loss there. So you will represent like that. So this is psi dash and then R dash. This is the small voltage drop and then this is. Similarly, this is a switch. So switch have an internal resistance. Switch have two type of losses actually. The switching loss, I will say the switching loss and conduction loss. So switching loss and conduction loss, these are two different. So whenever trigger, that time you will see some certain amount of loss, and then once the system is running continuously for a certain duration, so that time you are facing some certain losses. Those are these two things. So that's why we should consider a two resistance here. Similarly for the switches. Like that way, how generalized you can be building. So all the green color on this picture, we will consider as a unknown parameter. We have no idea about it. What is the value of that. So in the first phase, our target is to get the value of all these so that system equation will generate for DT. And then for this operation, definitely complete hardware setup will require. Then only you can do it. You can through the simulation it is not possible because if you will go for the simulation only, then this is not possible because in the simulations all these unknown parameters will be zero because all the components are real. I mean, standard ideal components, right? So ideal conditions, all the internal resistance are zero. Wire impact will be not there. Temperature impact will not there. So that's why don't go for the only simulation. So you should require one hardware setup. So in this experiment, this hardware setup we have used here. So you can see that. So here we have a different interfacing inductors. You will see this is the actually the converter. What converter we are using here? This one. This is the three-phase VSC, and this is single small boost converter also here. And then National Instrument controller board we are using here for the processing or maybe pulse generations, you can say like that. So those are here. Sensing units are the best here, like that way. The controller board in detail given like this. So this is the controller board. And then other side, this is the PV array which is linked with this one. This one is the digital tune platform, means here you will see the OpenRT and computer. And this one is not directly connected to this hardware setup. So this OpenRT and this hardware platform both are apart from, I will say, the 2 meter distance is gap between these two, and both are linked through the optical cable. Means through the cable, all the sensors informations are passing from this side to this to the OpenLT platform through this cable, and then all those passing the information is what? All the sensors information. What are the sensors are here? We all are the known parameters passing from this platform to this platform, and then similarly this platform can pass the information to the controller through the same cable. So the both are linked with the through a cable, nothing else. No physical electrical connections. You will see that only communication between these two. You can say that. So what are the components we have used here in the physical one and the controller one and all that? So those are given here, listed here. So that is not that much important, but yeah, I will say that the entire system is built for the 6 kilowatt. So this all the components we have taken according to that. The highest rating is 6 kilowatt. OpenLT side, we have used the communication cable, the cell twisted pair cable we have used. The length is 8 meter, right? So this one we have used here in this. A number of conductors are 3 pair we have used, which in between the hardware and DT model. And DT is running on our my OpenLT. So this one. So we have a OpenLT, so we are going for that. But if someone have a high processing computer, so they can go for that one also. So simple high processing computer is also efficient to do that. Only extra requirement will be the how you are going to feed the digital data inside that. So one board will require for the decryption, and then digital to digital conversion for your computer, like that way. So computer, through the computer also we can do these things. Not required OpenLT always, but yes, here we have OpenLT, so we have gone for that. So another thing is the calculation side. As I told, you have two options. One is the just assume data center, I will say the control room is 100% accurate. So with respect to that, you can measure your efficiency, and then that is sufficient to justify your output. Another is if you want to go for the actual data. So if you are going for the actual one, then you should consider the accuracy of each component. For example, if we are using here voltage sensor, then how many voltage sensors we are using? Now, what is the net accuracy of that? So if this is 0.9%, so the net accuracy is 0.5%. And then this voltage sensor is placed on a voltage sensor driver circuit. So driver circuits have additional 1% accuracy. So here the 5, so this is a plus 5%, like that way. So again, the current sensor, 4 current sensor we are using, what is the accuracy? So the current sensor driver circuit, and this is the controller side. The controller have FPGA board and all that. So what is the accuracy? Communication cable, again, we are going to lose some amount of power. So like that way, if you will consider all, even if inside the OpenLT, that is not going the OpenLT, you will see the digital to digital conversion. So, and this is a certain accuracy there, right? And also data is coming with a very high frequency, megahertz range. But in this DT, we are using 100 kilohertz, means we are scaled down the data and then we are using, because memory size is limited in our lab, so that's why we are going for the 100 kilohertz. But if you have a high processing computer system, then you can go for the megahertz range also. So this is 100 kilohertz. So again, we are going to lose some accuracy. This is 0.01%. So by considering all that, so if you will recalculate what amount of data we are going to lose in this calculation, so you will see that this will be around 15% data. So whatever the accuracy we are going to get in the control room, that will be multiplied with 0.1517, and then easily we can say that amount of data we are going to lose. Or you can say accuracy will be 84.25 whenever you are looking 100%, so that is 84.29 of that. So this is an approximate one, still again required a re-evaluation, and this is a lab prototype, that's why this is on the higher side. If the system will build for a particular component, so that time this will be hardly 5%. But in the lab prototype, we have gone for a higher rating, so that's why this is on the higher number side. But yes, we can go for that for the accurate calculations. Okay. Okay. So come back to our DT model. So in the DT side, the first is we are dealing with the time domain DT. So here first we will go for the physical system, then we will go for the equivalent electrical circuit, and then we will start applying one by one KVL KCL to write the time domain equation. Then we will go for the continuous time domain discretization. The differential equations we will generate, and then go for the discretization. During the discretization, here we are going to use backward Euler method. So many methods are available, right? Rangakuta or forward method. So many methods are used. But here we are using the backward Euler. Since we have observed that the performance is coming better, so that's why this is. Okay, so you can go for some other methods also, no issue with that. Okay, same network, going to write the case by case equation. So suppose going to write the case by case equation means here we will see the inverter. Power converter was the VSC. So here we will see on the power converter what is happening here on the power converter. So power converter side, total 6 cases will be. So 6 cases means these cases depends on the switching. For example, here S1 and S3 is on, S6 is on, and these are on, these are off. Case 2, 1 and 5 is on, and 4 is here on, and then the start off, like that way. So here you will see the total of 6 cases. So your target is case by case. Go in the case 1, start writing the KVL. And then during the writing the KVL, remember what you have to follow, all those green, all those unknowns you have to follow, right? All those unknowns you have to include. So write the KVL according to that. 6 cases, 6 different set of equations you will see. Okay, so not all equations, but yes, few equations I am showing here. So in these equations, so suppose this equation is your for the inductor current. So this is the inductor current. So in this current, you will see that all those things are considered here. So for example, you will see here RS1. RS1 means this is the resistance of switch 1. RLAI means this is the resistance of the filter interfacing inductor, phase A internal resistance. Similarly, RS6, this is switch resistance. Similarly, ILCC, this is the inductor current in the C phase. Like that way, it's all the unknowns anyhow should be here. So you will see that this is for the case 1 when the 1, 3 and 6 is on, and case 2, only 6 cases is possible. So you have to write all those equations. Okay, case 3, case 4, and see always you will see the, so these are differential equations actually. These are the differential equations. So this is a time domain. In a, here written I means I is t. It's a small I. This is t actually. That's why these all the equations are in a time domain. Okay. So and also for the DC-DC boost converter. So what inside the converter again we can apply the different KVL, KCL. So that is, and these are the interfacing inductors. So filter side also we can write in between the filter and grid all those equations. So after writing all those equations, next target will be to apply the discretization. So all these are already discretized. That's why this is looking like that. This is I plus 1. Otherwise, inductor current is very simple, right? L di by dt. We can say simply this is for the inductor, but you are not getting any D terminology here. Why this is? Because we have already discretized. So that's why this is. So already discretized. So for doing the discretization, what is used here? Here we have used this one, backward Euler methods, right? Even if you're somewhere, you will see the capacitor, and across the capacitor, you will see the as I say the inductor. Sorry, integration. Then take the differentiation both side, and then where is the differentiation? Then discretize that one. So like that way, you can mathematically deal with all these equations. So here multiple options are available. This is one of them what I'm talking. For the discretization purpose, you can go for any method. Even in the integration, if you have an integral equations, then you can discretize. So many methods are available. You can go for that one also. Okay, but anyhow, you have to discretize because you have a digital data, right? So that's why this discretization very important. And another tricky point is at the end of all these equations, you have to focus on these numbers, because at the end you know that you have few known parameters in hand. Known parameters in hand means what are the known data is in your hand. So the grid currents are known, right? Grid currents are known. PV current is known here. DC link voltage is known. Grid voltage is known, right? So PV voltage is also known. So anyhow, you have to write the equation for these known parameter, which is the function of all unknown parameters, so that you will generate this objective function to find out the actual value of all those unknown. This is the tricky point here. So which equation you should write and how many equations should write? So simple thing is that cover all those 6 cases, cover all those internal unknown parameters, and try to generate one objective function where we will compare the signal with the known parameters. Means first mathematically known and then actual known, compare together, generate the error, and through the optimization we will try to reduce the error, and at the end we can easily get the all the unknown parameters where error is minimum. Error is what? Error is in between the mathematically, or we can say the calculated known parameters and actual known parameters. Actual known parameter is coming from the sensors, and actual are and then calculated one is through the mathematics. So gap between these should be zero in ideal condition. And once it is zero, then it means all the unknowns are known for you. So this is the basic tricky point here. So equations are according to that. So that's why if whenever you will see my papers, not my papers, my students' papers actually. So all those papers, always you will see a huge mathematics. Those mathematics are only 10 and 20% of that. Because here these equations and mathematical terminology is very much important. Then only you can get the values of those unknowns. Okay. And once your equations will ready here, then you will this is looking simple, but this is a function of what? For example, in this equation, this information is coming from sensor IGAI, but IGAC is a C means calculated one. This calculated is coming from where? This set of equation. This set of equation is the function of what? All unknowns. These are the unknowns. These are unknowns. These are unknowns. So this is the function of all that. This one is the function of that, like that. Maybe this one is the function of few set. This one is the function of few set. This is the function of few set. But when you will see all the entire equation, all will be inside here, right? Like this way. And then you will start using any meta-heuristic technique you can utilize here to get the minimum value of that. Okay. But again, you have an option for the meta-heuristic technique side. You can go for according to your choice. For example, here we have used the Coulomb's electromagnetic field optimization. See here, when you have a number of variables are more, and then number of variables are more, and then and your your meta-heuristic technique is highly randomized, right? Then chances is that it will require some certain huge time to settle down, because here data is coming with a 100 kilohertz speed, right? Suppose you have decided that you will trigger your system, or you will finish your mathematics within a second or within a 5 seconds, suppose you are saying. So what it means? It means that data is coming with a 100 kilohertz speed, and you have taken 5 seconds. 5 seconds. It means 500,000 data. Means indirectly 5 lakh data you are going to get for one through one sensor. You have total of known parameter is 9. 9 into 5 means 45 lakhs data you are going to get, plus 1, because all these numbers are, all this data is a time stamp data, or you can say the sequentially data. So again, one additional information will also there. So indirectly you will see that total 50 lakhs data from your 9 sensors you are going to get within a 5 seconds. And anyhow you have to finish your all this calculation within the 5 seconds by using these 5 lakh data. So anyhow you have to converge within a time frame, then only this will work correctly. If it is here required huge time, then those techniques will not help you, because time is increasing, data size is increasing. You cannot miss the data. If you miss the data, dynamic will miss, tangent informations will miss. Okay. And then another side, you can say, okay, I will go for the 100 second, sorry, 10 second. Okay, you can go for that, but data will just double of this, right? So required a huge that size over your processor. Okay, so that's why here the computational cost is increasing with time. So you want to minimize that. So you have to finish within a high time frame. So one side data size will decrease, then computational cost will decrease. How you can decrease the data size? You can say that, okay, I will not go for 100 kilohertz. I will go for the 50 kilohertz. So definitely data size requirement will be 50% of that. But your switches, the DC capacitor, sorry, DC-DC converter is operating on 20 kilohertz, right? And then you are playing with only 50 kilohertz. It means hardly 2 or 3 data you are going to get in one switching cycle. So that will not sufficient to decide the behavior. So one side you will reduce this, then performance will be, transient performance will be. So that's why you should play with in between. So anyhow, we have taken the 100 kilohertz to do these things. And then we have chosen this algorithm. So you can choose the algorithm on the basis of this. So what time frame you have decided, and this algorithm is capable to converge within this time frame or not. So here I've taken this one. You can go with the other techniques also. Another things, this is not important, but I want to slightly pass it, because whenever you will see that, so that, or you will decide that, okay, I will not go with the classical one, I will go with some modified one or hybrid one, and again you have a challenge. If you are going to hybrid one and modified one, directly you cannot say that, okay, this modified and new optimization technique you are going to use for your system. So that time you have to first test over the benchmarks. So these benchmarks is mainly for the optimization technique, classical metaheuristic optimization technique. You have to test over these different benchmark functions. In these benchmark functions, you will see the benchmark function is given, and result is also given, and range is given, and you will test, and then results will compare. So these are those functions, actually unimodal, multimodal benchmark function, and then you will compare with the classical one. Then only you can confirm, okay, I'm going to use my technique with the whatever the system you decided. So this is the basic way, and this is not important for the DT, but yes, I'm saying that directly don't try to use, first go for the check and then conclude and then focus over that. Another is also control technique side. This, you can use any control. Again, DT is not dependent on the control, what control technique you are using. Okay, so you are using the DQ controller, or maybe you are using any advanced cladding mode or model predictive controller, no issue with that. You can go with any control technique, right? But so whatever the control technique you are using, and what is your objective? If your objective is only for the monitoring, then any control technique will work for you. But if you are planning, okay, in extreme cases you will give the command to the system to take the counter action also. So that time control technique should be in such a way so that receive the data and take the action accordingly. Okay, that's what. So the selection of control technique should be according to that. For otherwise we have hundreds of data. For example, you can see the all these are the control techniques, and more or less all are working fine, but these are for the primary control, and in with any control technique you can go for the DT, but the communication will miss, right? Communication miss. So that's why here you can choose according to your choice. I'm also not going to focus on the control technique, so because in initial stage when you are going to form a control technique, form a DT, so that time control technique we will consider as a classical control technique. Whatever the control technique is there, that is fine for us, so we will go for that one also. Okay, otherwise we will think about some advanced control technique. Leave the control technique portion. So control technique is running. For example, control technique is unit template based. So the first stage generate the unit template, and then generate the feed forward terminology for the PV, and then go for the DC link voltage maintaining means generate the loss component. Also, if you load, then load current, net active load current component. Then you are going for the final grid current reference you are generating, multiplying with a unit template, and then this is. If this is a DQ controller, then you are going for the load, your D and Q component, and then accordingly you are generating, you are using the PLL for the for the equation purpose, and then you are multiplying and then generating the grid current reference. And then by using any hysteresis controller, you are generating the pulse. But these things will be inside the controller, which is already built by a third party, because this is on the initial level with load. If we don't have load, then any other smaller control technique will also work. No issue with that one. So I will suggest at initial stage, don't focus on the control technique, because control is already on the hardware platform. So those is already in use. Only focus on these equations, what the mathematical equations you have generated for the plant, and then focus on the sensors information, and then your optimization technique to try to match with the waveforms. That's it. So here you will see this section is your hardware side, this side is your optimization, and this one is your DT side. Means through this sensors you are feeding the data in the mathematical model. Mathematical model is going to your optimization technique side. Optimization technique is converging by using your waveforms matching. Once the waveform is matching, accordingly what information is getting, and then this through this side you are again back feeding to your digital model. And then once all the unknowns are known, so that time digital tune is ready to use for the purpose. What should be the purpose? Maybe the loss, maybe your accuracy, or maybe the performance, whatever. What is your target? You can get according to that. Okay, so few results I'm trying to showcase here. So result side, in the time domain side, suppose irradiance is changing, then you will see that. So these are the known signals, right? Means directly coming from the sensor. So those are here, means voltage, current, and then PV side. And then control signals. So alpha, beta, what are the control signals internally happening? But for the plant level, this is not available to you. In the lab, whenever you are doing, then only this is available to you. Okay, because controller is also built by you, so that's why this is available. But if you are directly going for a plant, so that time this controller information will be inside the plant, inside the controller of the plant. So and that will not accessible to you, so that time you will not see these information. Okay, another most important is this portion. So this here you will see two part. One is the measured signal from the physical system. On other side you will see the output signal from the digital tune. Measured signal means what? Measured signal means, suppose you are talking about inductor voltage, inductor current. So you temporarily you have placed your probe there to see the waveform across your inductor, to see the current across the inductor. So that is measured signal. This is temporarily. Another is this is the output signal of the DT, and then this one is this signal generated through the DT, and both you are going to match. Similarly, this is the inductor current, both you are going to match. Okay, so like that way. So one side you are measuring by using the additional external probe without disturbing or cutting the wire and all that. So you are just measuring temporarily and then comparing with the DT, and then on that basis you are going to decide the digital or DT similarity score, right? So you can see that. And then finally here what information you are getting, this is 97%, 97.1, 96, and like that. So this is the achievement of this in this case. Similarly, different cases. So case will change under grid voltage. Same thing you will do. So you will see the different accuracy under distorted conditions also, when the grid voltage is distorted, and then how the system is going to operate. Here the different cases means we are trying to analyze the dynamics performance. So during the dynamic condition, our DT is capable to capture those waveform or not. Here the DT objective is not to generate pure sinusoidal current. That is the objective of controller, which is already there. Here the DT is to analyze the waveform. Waveform is waveform we are capable to uh, represent the actual waveform or not, or estimate the actual waveform or actual performance or not. That is the objective. Even in the distorted grid condition, if grid your conductor current is like this, then DT is also showing that yes, this is inductor current. Okay, So if your DC link is suppose oscillating, then GT should inside the DT also that should oscillate like that. So like that way we have achieved 95.7. This is the worst one. Like that way in the time domain condition. Another is the component variations with the time. With the time, component will vary. Component means capacitors. The capacitance will decrease. Inductor side inductance will decrease. Right. So with time, these components are going to change. Then again, our system is capable to predict those changes or not. That is the main objective here. So for that purpose, this test performed. So inductor variations. So what we have done, we have taken a tap changing transformer across our inductor, interfacing inductor, and then during the running condition, intentionally we have changed the tap. And then what happened? And target is, so our DT should predict that okay, inductor has changed. Similarly, in the DC link capacitor side, we have placed the multiple capacitor in parallel, and during the running condition, we have changed the capacitor, or we have removed one by one capacitor. Target is, so our DT should predict, so okay, capacitor is changing. So this is in a real time. So those experiments is performed also. So you can see that one. The accuracy of the component variation prediction is 97%, 98%, and this one is based on what? This one is based on the multiple factors. So because maybe both can happen together or something like that. So here we have used the AI. So by using the AI and by monitoring the different features, we can say that. For example, in case of inductor, you will see power loss, grid power, TSD, and then internal resistance of the inductor, inductance, actual inductance of the inductor. We have monitored these things. But inside, when we have gone for the capacitor, then power loss, power grid, TSD, DC link voltage, and DC link voltage, internal resistance and capacitance, and fluctuation. All those information is used to decide what is happening there and who is responsible for that. And by using the AI, we have predicted, okay, so this is because of the capacitor and how much capacitor deterioration is here. But yes, this is intentional, but target is to predict that one. So this is result is given here. Another is the stability monitoring also we can do. Once results are on the data is in your hand, then by using your Lyapunov method or Jacobian methods, we can monitor the stability of the system also. That is the basics one. Anyone can do. So this is your time domain one. But one important expectation, I will say the marking point is here. What is the average output, or I will say the performance we have recorded is 96.51. Another approach is frequency domain side. Frequency domain, everything will be same. Everything will be same here. Only extra thing what you are going to do, once you will write the differential equation, then you will start. First of all, you will reform the equations in a S domain, then convert into S domain to Z domain, because S domain is a continuous domain. Then you will convert into Z domain, and then you will apply your this DT modeling. So this time S to Z just-in-place transformation is used, but you can go for some other methods also according to your choice. Okay, so similar again, everything will same as I told. So case by case, you will derive the equations and all that you will do, and then you will write all the equations as in S terms and Z term. So this is the discretized one. That's why you will see the Z term is everywhere. Always everywhere you will see the Z term. This is discrete one. Final equation. And once the final equations will over, again back to the same objective function. Then you will same objective technique you will apply, and then again you will try to predict all those unknown values. This is very similar like a time domain. But extra thing you will see here, when you will go for the result section side, then this time you will see that the accuracy is a little bit better with respect to the previous one. Previous where we were suffering with the 96 and 96.5, 97 hardly. But this time you can see the 98, 97.75 or something like that. In the worst condition also 97 and something. In a distorted condition also, means more or less always you will see 97%, 97.5% plus we are getting the result. Also this time with a high efficiency you will record it. Also in the time capacitor side also this one. Means in the frequency domain, you will realize that our result is much better with respect to time domain. But problem in the frequency domain is scalability. If you will try to add additional component here, then first of all you will go for the physics based equations, then you will rewrite the equation, then discretization, and then all that. Means a huge change will required. But in the time domain, simple component is adding, differential equation will slightly change, and then also you can uh, make a closed loop there and to capture those unknown parameters, and easily you can utilize that one. Means time domain is very easy to implement or scale the plant, but frequency domain is little bit complicated because of the S domain and Z domain, but accuracy wise you will get an advantage. These two are value for the actual application side, means if you want to for the actual plant side. But so that's why you will see the average output is 98% plus. Last one is the data driven digital tune. Data driven digital tune is not for the actual application. This is for the research purpose only. So this one we build up for the research where the plant is not available or any plant is not ready to share the data. So that time if anyone want to do the research, then how they will do that. So for that purpose what we have done, we have first of all our target was to generate the data. So we have generated the data, raw data, and then once the raw data is ready, then we have gone through the bad data detections to detect the bad data, and then and identify the corrected data, and then identified corrected data will be re approximated by using the ML technique, and then by using the ML technique we train our model and then predict the performance what we are expecting. So this is the basic structure of the data driven digital for the lab purpose. So for that purpose, what we have done initially, so we have complete system we have done for the 40 cases. We have divided into 40 cases. So three cases we have taken, three major cases we have taken. Normal condition, irradiance change, grid. Means here we have assumed that everything is perfect. Only input output is varying. So what are the things is possible? So here we have taken 25 cases. Every component is same, every load and everything is same. Only input output side source and grid is varying. So what are the things is happening? 25 cases we have taken for that. In each cases we have recorded the all known data as well as unknown data. Similarly, other one is the component internal parameter verification side. So here in the inductor we have varied the different inductor. So we have recorded inductor, capacitor, both side inductor. So we have changes those 15 cases we have developed and then recorded the data. Another is the sensor malfunctioning. So here two current sensors are malfunctioning, three current sensors are malfunctioning, seven current sensors are malfunctioning, or voltage side and voltage and current together also. So like that, with total of 30 we have cases we have checked out. Means total of 70 cases, and then total of you will see the 9 known, one time 10, and then 30 unknown is 40. So total of 40 set of data you will see in each. So and then initially we have placed the data on a given link. Also in the ITP transaction we have given the link there in the paper, as well as very soon this information will be available on the ITP dataset repository. So actually the size is very large. So here the approximately required, I will say the 100 GB data we have generated, right? And we are trying to dump in the IEEE so that everyone can use anytime for that. So this one. So in this data side, how you will do, what type of research you can do that. So that is the first data for bad data detection side. So this total of 30 cases can be used for that. So here how you will detect this one. First of all, the basic process is the range check. Then you will go for the your mesh. Then you will time switch continuously. Then you will see the power cascading. So means the power check. So range between the power is not or not. Similarly for the switching consistency. So for example, we know that we both in the same leg both switch cannot be on at a time. So those things we can also check. And then finally we will go for the physics based data consistency validation. Means a small KVL and KCL we can apply to see the data. You can node by node check. We can say the nodal analysis. You can simply can say that. So through this way we can predict what is happening or wrong with the data and then identify where is this. So this type of research we have done, and then you can apply any machine learning here given the transformer decision, but you can go for any machine learning, right? And this machine learning will for the training purpose, because whatever the data you have, target is to train and then validate and then test. So whatever the data you will download directly from there, so 80% data give to for the training, 10% for the validation, and then random 10% keep secret for your testing. So during the testing, known parameters means sensors data will consider as a input variable and other will consider as unknown parameters. And then once you will get the unknown parameters, simply match and see the error, and you can see the accuracy of the model. So like that way, these things are working. So why this method? So you can go with the basics of the machine learning and leaving this. So according to your choice, you can pick that one. Okay, so operation is very similar like that. Okay, so we have a data set. So here we have generated the data set. Data set is available here. So take this data set, first check the bad data, but even in the data set already we have written where is the correct data, where is the accurate data. So simply you can go for the accurate data. So if you are directly focusing on the DT, or you can go with the bad data detection also. And then take the data and then train here. 80% training, 10% validations, and testing is for the 10%. So on that basis, you will get your unknown parameters. Once unknown parameters are in your hand, it means DT is ready. Like that way, you will do this research. But this one is only for the research purpose, not for the actual applications. The accuracy is here 96%, 95%, something like that. Here is accuracy is low because here we have what data is recorded on the 100 kilohertz range only, right? So and then because of that, all the transient or dynamics, I think not we had capable to capture. So that's why little bit this is on the lower side. But this is okay. This is your digital tune finally. So different malfunctioning, or sensor malfunctioning, current malfunctioning, all those things you can do by using this data. Accuracy is 96.2%, which is lower with respect to that. If you will compare all three, discrete time domain, frequency domain, and data driven side, discrete domain is good for the application side. This one is for the plant is not ready to provide the required data. So then there you will use the data driven DT model. So this one is not for the actual plant. Go with the actual plant this side, physics based, that time domain and frequency domain. Another is the model side. Here we have used the backward euler, here we have the trusty, here we are using the ML model. Accuracy 96 around, here 98, this is 95. So this side, this may be higher also, it will depend on the accuracy and then machine learning selection. If maybe, so maybe the advanced machine learning can be used to reach the higher rating, higher accuracy. So this is completely depend on the machine learning, nothing else. Scalability is here high because this is easy to model, so that is scalability. Here you see the low performance efficiency was high, but this scalability is low because of the complexity on the equation side. Also the system burden also here is high. So you will see 14 to 18% CPU loading per cycle in the frequency domain, but here this is low, 8 to 13%. And time per cycle is also here required 5 milliseconds to trigger, and here 5 to 8 milliseconds is required to converge. So this is also one of the issue. Okay, but through this we can conclude, okay, this is GT and you can use it for the any application. But for the future scope side, if you want to do that, what are the things we have not done yet? So you can think about that. So missing part in this entire research is effect of temperature variation is still missing in the research. We have not incorporated. Why? Because at this time we have assumed that we don't have capability, we don't have authority to place our any additional sensor in the system. That's why this is. But just assume if system is allowing you to place your temperature sensor, then we can consider it. So if we will consider the temperature variations, then accuracy will be much better. So those things we can do means we will place our temperature sensors across our switch and across our component, and then we will take those temperature based effect also on our system. Definitely temperature information will be considered as a known parameter and others will be unknown. Then that time unknown will be more beneficial, and we should consider that one also. Okay. Another is the uh, here the load dynamics is not considered on the PCC. That is also one missing point. So can think about that one also. And also the converter is a very classical converter what we have taken. Someone can think about that. Any additional because converter is changing. You know the cases are changing also. So the converter is single phase. So the number of cases will be only 4. And then similarly you will see that converter will be changed. Number of cases are going to change. So think about that one also. And another is the switches. What the switch we have considered, so that time turn on, turn off, and body diode loss, all three should be considered for the each switch. Means each switch have 3 variables, but we have considered only 2. So that time equation will be more generalized. And extend the system for the high rating, high power rating. Means during when we will go for the high power rating, so that time cable loss, cable have on resistance, right? So those should also we should consider. So those are not considered, which is we are planning to think for future. So that time we can you can also consider for the future applications. Based on all this research, whatever I have shown here, so these are the papers. Around this is the recent one, all in 2025. All 10 transactions were in 2025 we have published, all related to this digital tune based on that in different journals. So, and these are the my PhD students who have done, we have worked on this. These are 4 PhD students who are close to submission. 3 already have submitted and 1 is going to submit soon. So this is related to them. Thank you. If anyone have any questions, I'm open for that. You can ask.
Thank you, sir, for your insightful lecture.
Thank you.
Sir, I have some questions.
Yeah, sure.
Sir, first question is that we have considered the ESR part of for considering the losses.
Mm-hmm.
So suppose we are not we are dealing with ideal system.
Mm-hmm.
We have developed an algorithm.
Mm-hmm.
Then to work on DT part, digital to twin part, then is it necessary to consider the ESR systems? ESR.
See, first, uh, uh, see, ideally, what is your objective? Actually, in DT side, if you are going for the only performance matching, right? Then that time ESR is not that much important. You can leave that one also. But when you are going for the means stability analysis or some many other portions, and then there in the algorithm you should include those one, because performance matchings have only basic KVL KCL or network equations if is sufficient, and then some portion is suppose missing. For example, here temperature portion is missing, and then suppose we have also leave the your conduction loss, and then both loss we have considered same, and then we have gone through that, but still we are getting the 96% efficiency. So like that way initially you can start, but yes, for more generalized you should consider all possible things in actual scenario, but you should start, you can start with a basics one.
Question. From real-time plant view point of view,
Mm-hmm.
is it always necessary to connect the system to the digital twin?
Yes, yes, all time. That because all the sensors should be connected to the DT all time. It not mean that so you will go with the plant and connect there. So DT directly connect to the control room, because in every plant have a one control room where the performance are visualizing or monitoring, right? monitoring means what? The waveforms are completely visible on the screen, and then operator is sitting there and then looking on the screen and then seeing the performance. So those informations can use in the data. Not necessary to go, especially in the plant level, and then one by one you are going to integrate. No, just in the control room, through the control room you can do that. But yes, 24/7 your DT should connect to the your control room or maybe plant. Then only you can see the performance.
Suppose we are using DSpace we are using or pivot controller we are using. And in those cases also we have to connect the system to the controller.
Yeah, definitely. Suppose you are using the DSpace and then DT. So DSpace and DT both should connect it. Then only you see one side your suppose DSpace is running your hardware, right? So the hardware information should go with the DT. Then only DT will go for the optimization technique to minimize the results and all that.
So my
Like
question
that.
is that if you are having a DSpace or Vivek, then how digital twin will be an advantage over those Vivek and
Okay. No. DSpace is a different thing. DSpace is a controller, right? To generate the pulse for your converter.
yeah.
So DT is a different thing. So DT will be on your computer or maybe in your GPU or whatever. So these two are completely different. DT cannot run on the DSpace.
Okay, sir. Okay. Sir, one more question.
Yes, sure.
Sir, from cyber attack point of view, is there an advantage for digital twin?
Yeah, definitely. So many advantages here. So here you have an option. So here you are getting the 24/7 data. You are connected to the system. So what you can do that for the cyber security research side, you can keep features, you can store, right, and keep for future uses, and then track. For example, suppose you are just for a simple example, I have an inverter, and then day one when I'm operating the inverter, and suppose the inverter size is 10 kilowatt, and then day one, initial days, I realize that inverter efficiency is 95%. It means that 500 watt is the loss, right? Basics when the new inverter when I purchased. Fine, I have recorded and keep for the future use. And slowly, when the time will grow, definitely the losses will increase. 500 become 550, 600, or something like that. Suppose one day someone will try to manipulate the data, and then in the converter start performing much better, looking like a much better. Efficiency is 98% after 2 years of operation. What it means? Then definitely somewhere is wrong here, right? So like that, this is one example. So by keeping this triggering data, you can predict in future what is the cyber attack, what is the wrong happening here. Where is the wrong? That is another thing, but definitely some wrong is there. Maybe the calculation wrong, maybe the data manipulation, or maybe your system malfunctioning, or maybe a cyber attack. But yes, wrong is there. You can confirm because you know that the day one this system was 95%. After the 1 year of operation, how this can be 98% efficient? Simple. So this is one example. Like that way, you can keep the different key data record for future users and use those things for the triggering or identifying the cyber attack.
Thank you, sir. Thank you very much.
Thank you.
I request participants to, if they have any questions, to then they can raise their hands. I don't think they have any questions.
Okay. Okay, no question, no issue. So even if you are in future, anyone is going to implement this one, and then facing any issue, you can write mail directly to me, and I will definitely try to answer you. No issue with that.
Thank you, guys.
Thank you.
Thank you, Dr. Nishant, for delivering a wonderful lecture on various aspects of digital twins and wonderfully explained from fundamentals beginning to application. So, on the behalf of AICT Academy, MNIT Jaipur, and myself, I thank you a lot for delivering this lecture. Thank you so much, sir.
Thank you, sir, and then sorry for the disturbance for 5 minutes in between.
That's it.
So thank you, sir. Okay.
Thank you. Okay, so we take here 5 minutes break and we'll start the next session.